This video is for the lab Build an Accelerometer. And I know in the directions it tells you to build the accelerometer out of a baby food jar, but you might not have that at your home. That's totally fine. We're gonna have to improvise on a few things. What I had laying around my house was a variety of small jars, but you don't actually have to make it out of a jar. You can make it out of a cup. I was able to find a jar that had a lid that fit it. What I did was I tied a paper clip to a thread and then taped that to the bottom of the jar to make the motion detecting portion of the accelerometer. An option that you could do if you don't have a lid or if you don't have a jar and you just wanted to use a drinking glass, you could take the lidless jar or drinking glass, take a cardboard box, you could trace out the circumference of the opening, make it a little bit larger than the opening of the glass or the jar, and use that as the lid. And then tape your thread. If you don't have a paper clip, find something that doesn't dissolve in water and tape that to the bottom of the thread. We're just gonna have to improvise as we move along. Any way you construct it, when you're all done, this is the basic part of it. The next thing you have to do is add water to the accelerometer. So I'm just gonna step over to my sink and I'm gonna put water into my jar, put the paper clip in, and now I have my accelerometer created. The purpose of an accelerometer is to detect acceleration. And as you may recall, acceleration is a change in speed, direction, or possibly both at the same time. The instructions ask you to do a variety of things with your accelerometer and observe what goes on. I'm actually going to start off with the part that says, push your accelerometer so it slides untouched across a table and comes to rest. Explain in words and pictures how the paperclip shows acceleration speeding up. So I'm going to take my accelerometer here and I'm going to give it a little push with my hand. And when I do that, I notice that the paperclip initially swings back toward my hand, and when the jar comes to a free sliding rest, I see the paperclip swings out away from the direction of my hand and finally goes back up and down. So in this case, where the jar is speeding up, initially the paperclip swings back towards my hand, swings out away, and then returns to its original position. It asks me to explain this with a diagram as well, so I'm going to draw a free body diagram over here. It doesn't matter whether you're depicting a jar, a cow, a car. Everything in a free body diagram is simply a square. So this is how you represent the object. And another thing to think about is in physics, in a free body diagram, you're just thinking about the forces that are acting upon that one object. In prior lessons, you've learned about something called the normal force. And this arrow is representing the direction and the magnitude of the force. Since there is a supporting force from the countertop up on the jar, this arrow is representing that supporting force, which is called the normal force. And I'm just going to represent that with an Fn for normal. There is an opposing force on the jar, and that's the force of gravity. So I make, oops, I don't like that arrow, it's too curvy. So I'm going to make the other arrow equal in length to represent equal in magnitude and opposite in direction, and I'm going to say F sub g to represent the gravitational force. These two arrows are supposed to be equal in length to show equal in magnitude. I did the best I could. Okay, now I'm diagramming a push, a force applied, and the friction that is opposing it. So if, let's just say I have pushed the jar with my right hand from the right hand side, I'm going to have an arrow here representing the applied force from my hand, And what is opposing the force from my hand? Well, it would be the force of friction. And because the force of friction is less than the force from my hand, because I'm accelerating, I'm speeding up the jar, the force of friction arrow is going to be shorter than the force applied. And if I were to be looking at this paperclip's behavior inside the jar, if this was my hand pushing on the jar, initially I see the paperclip swinging back towards my hand. Now, in the second part of it, it asks me to say what's going on with deceleration. My hand is no longer applying a force on the jar. The jar is sliding to a rest. And as I mentioned previously, I see the paperclip swinging out away from my hand where it had been, and then eventually it comes back to rest. Technically speaking, slowing down is also acceleration. Commonly we call it deceleration, but any change in speed or direction, that's acceleration. So slowing down is also acceleration. What would this look like for a free body diagram? Okay, for that case, I'm going to draw my rectangle again, representing the jar. Once again, I have my normal force, and equal but opposite opposing it is the force of gravity. My hand is no longer on the jar. So in this case, I don't have to put the applied force arrow on it. But I am going to put in my force of friction. And what I see happening is that the paperclip, which technically speaking on a free body diagram you wouldn't be drawing in like paper clips and strings, but I just want you to see how that would look. The paper clip is going to swing out before it comes to rest again. And this is what the free body diagram would look like for that. So imagine I have pushed the jar from this side. My hand is off it now, so there's no more applied force. Because of the force of friction, the jar slows down and I see the paper clip swing forward. Excellent, we're almost done with this lab. The last thing the lab asks you to do is move around with your acceleration, your accelerometer, and see what happens. Anytime this paperclip on the string wiggles or moves or swings, it indicates that acceleration is occurring. Acceleration means that forces are unbalanced. I notice when I turn my body to my left side, I see the paperclip swing to my right. And when I turn my body to my right side, I see the paperclip swing to my left. So obviously me changing direction is causing acceleration to happen. You've seen this occur before if you're in a car that has like fuzzy dice or something happening from or hanging from the rear view mirror. That's an accelerometer that's in people's cars. You turn a corner, you see the dice swing around. Now what happens if I take this jar and I just push the jar at a constant speed across the countertop? I notice that by and large, for all intents and purposes, the paperclip just hangs straight up and down. It doesn't swing out. Since the paperclip remains up and down, that would indicate there is no acceleration. The forces are balanced. If I were to twirl around, what I see happen is the paperclip swings out in an arc. I can just do it like this. And so once again, the paperclip moving is indicating acceleration. I hope you had fun building your accelerometer. I hope you understand that when the paperclip in the accelerometer moves, it's detecting acceleration, and that you understand acceleration is a change in speed, direction, or both due to unbalanced forces.